Okay, so now we are going to discuss chapter 24, yet more analysis, and we will talk about the continuity. So I'm going to introduce you to the notion of continuous functions of real numbers. This is a topic that deserves a whole book to itself, but I'm giving you this little tester here for several reasons. First reason is that first notion is the right setting in which to prove the existence of nth roots of positive real numbers, which I promised to do way back in chapter 5. Second one, quite quickly develop enough theory to prove a famous result called the Intermediate Value Theorem, which sheds quite a bit of light on the great fundamental theorem of algebra, which we have stated in the chapter number 7. And last, the idea of a continuous function provides yet another example of something natural and obvious sounding being turned into rigorous mathematics with fruitful results. So you can assume that the material in this chapter is perhaps at a higher level than most of the rest of the book, but it will repay study and hopefully serves as a useful introduction to your next course in analysis. Okay, so let's define the continuous functions. So let's say f be a function from real numbers to the real numbers, and let c be a real number. We say that f is continuous at this real number c if we can make f of x as close as we like to f of c, provided we confine x to being in a sufficiently small neighborhood of c. In other words, we want to show that the limit of f of x is f of c at x tends to c. We shall make the phrase as close as we like and sufficiently small neighborhood precise in rather similar fashion to the definition of a limit in the previous chapter. So let's give the formal definition. Definition: a function f from R to R, real numbers to real numbers, is continuous at a point C in R if the following holds. For any epsilon greater than 0, there exists delta greater than 0 depending on epsilon. So you can write depending on epsilon such that mod of x minus c is less than epsilon, then mod of f of x minus f of c is less than epsilon. Sorry, mod of x minus c is less than delta, then f of x minus f of c mod is less than epsilon. This is the formal definition for the continuous function. And now we can say, in other words, f of x can be confined between f of c minus epsilon and f of c plus epsilon, provided x is confined between c minus delta and c plus delta. Now, we always understand more by examples. So let's give an example. (24.1). So number one example is the function f of x is equals to x is continuous at every real number or point, every point in the real numbers. To see this, let epsilon is greater than 0. We take delta to be epsilon. Then we say x minus c is less than delta, then f of x minus f of c, which is nothing but x minus c is less than delta, which is epsilon. Okay, perfect. Number two, any constant function f of x is equals to some k for all x in R is continuous at every point in R. Okay. Number three, you can say this is exercise. Show it. Let's define a function f from R to R by f of x is 1 if x is in real numbers, sorry, in rational numbers, and 0 if x is not in rational numbers. Okay. Now we claim that f is not continuous at any point in real numbers. We claim that f is not continuous at any point in c in real numbers. Now to prove this, we must provide a value of epsilon greater than 0 such that there is no delta satisfying the definition. So first, let there is c in rational numbers. So f of c is 1. Now take epsilon is 1/2. Now for any delta greater than 0, we know by definition, by proposition, proposition 2.5, that there is an irrational number r between c minus delta and c plus delta. There is always a irrational number between two rationals. You can say that. So then r minus c is less than delta, but f of r minus f of c is actually nothing but 0 minus 1, which is 1, which is greater than epsilon. So there is no value of delta which works for epsilon is equals to 1/2, showing that f is not continuous. At C. Now let's take C not from the rational numbers. So we have f of c is 0. We again take epsilon is equals to 1/2. This time we observe that at any delta greater than 0, there is a rational number s between C minus delta and C plus delta. Then we have S minus C is less than delta, but f of S minus f of C is equals to 1, which is greater than delta, showing that f is not continuous. At C. Now, this is the proof. We say that a function f is continuous on real numbers if it is continuous at every point in real numbers. So the point is, we say that a function from R to R is continuous on real numbers if it is continuous at every point C in real numbers. Okay. Now, roughly saying, this says that the graph of the function f is a continuous line which can be drawn without taking your pen off the paper. But this could be misleading also, because there are continuous functions whose graphs cannot even be drawn. So from the example 21.4, we see that constant functions are continuous on real numbers, and also the function f of x is equals to x is continuous on real numbers. Having obtained these simple examples, we can build up many more using the following sum, product, and quotient rules. So let's give the rules. So we have a proposition. (24.1), which says that let f and g be functions from R to R. So the functions one, which we call the sum rule. If f and g are continuous at a point C, then the sum f plus g is continuous at point C. 2, which is the product rule, says that if f and G are continuous at C, then the product function fg, which is defined by f dot g of x, which is nothing but f of x, and g of x is continuous at C. And the third rule is the quotient rule. It says that if f and g are continuous at C and g of x is not 0 for all the values of r, then the quotient f over g is continuous at C. Now we can prove this proposition, but you can use it without the proof to solve the exercises and the examples. So we'll leave the proof for the readers, and let's solve the examples and exercise, some examples. Okay, so the first example is number one is, we know that f of x is equals to x is continuous on R. Then by the product rule, in proposition by the product rule in proposition 24.2, by the above proposition 24.1, number 2, the function x to x square is also continuous as x to x cube and in general x to x power n for any positive integer n, for any n in the positive integers. Also, constant functions are continuous. So the product Product rule also shows that for any real number C, the function x to c into x power n is continuous. Hence, using the sum rule, we see that any polynomial function x to an x power n plus an minus 1 x power n minus 1 plus an a1x plus a naught, where ai's are also real numbers, is continuous on reals. Okay, perfect. Now, example number two is, consider the function g of x, which is x cubed minus 5x squared plus 2 over x squared plus 2x plus 2. Now the denominator x squared plus 2x plus 2 is nothing but x plus 1 whole square plus 1, which is greater than 0 for all x in R. So G is continuous on R by the quotient rule. Perfect. Now let's take number 3 and consider the function h of x is 1 over x, and if x is not 0, and 0 if x is 0. Now, if you look at this function, you can say a slight generalization of the quotient rule, a slight of the quotient rule shows that h is continuous at any point C not 0. But is H continuous at 0? This is the question, and the answer is no. Zero at 0, this is not continuous. To see this, let epsilon is 1/2, and whenever delta is greater than 0, we choose not the whenever, whatever. We choose there exists a value of x with x minus 0 is less than delta, such that h of x minus h of 0 is greater than delta, is any x with mod of x less than 2 will do. Hence, h is not continuous at 0. Perfect. And now we will give the intermediate value theorem. Now, this famous theorem says that if f is a continuous function, and a comma b are real numbers, such that f of a is not equals to f of b, then f takes on all values between f of a and f of b. If we think of a continuous function as one whose graph is continuous line, this seems obvious as a continuous line form from a comma f of a to b comma f of b. Will surely pass through the points with all the possible y values between f of a and f of b. However, finding a rigorous proof is not all obvious, and the following proof is one of the trickiest in the book. So let's present the intermediate value theorem and then prove it. 24.1. Intermediate value theorem. The statement is let if is a function from real numbers to real numbers be a continuous function on R, and let a comma b are real numbers with the condition that a is less than b, and f of a is not equals to f of b, then for any real number comma between f of a and f of b, there exists a real number c between a and b such that f of c is common. That means that this function is continuous at c, which is a point, which is a real number between a and b, and the value of the function at which it is continuous is gamma. And let's prove this theorem. So it's a big one, but we'll try to be precise. Let's assume that f of a is less than f of b. Let's assume that f of a is less than f of b, and we are doing the case so, and the case where f of a is greater than f of b will follow by a simple trick which we give at the end of the proof. So we have f of a is less than gamma and gamma is less than f of b. Now define a set of real numbers as follows. S contains real numbers such that x is less than or equal to b, and f of x is less than gamma. Okay. Now, surely, then S is not sorry, S is non-empty, is A is in S, and S has B is an upper bound, is an upper bound. Therefore, by the completeness axiom, which we have discussed in chapter 24, S has a least upper bound now let small c is the least upper bound of the set S. Okay, now we shall prove that the f of c is gamma, and which will prove the theorem. Okay, so suppose first that f of c is less than gamma. Now let epsilon is gamma minus f of c, which is greater than 0. Now, as f is continuous at c, there exists delta greater than 0 such that x minus c, absolute value of x minus c is less than delta than f of x minus f of c, and its absolute value is less than epsilon, which is gamma minus f of c. Okay, perfect. Hence, there is a value, x, which is c plus delta over 2. And for instance, such that f of c plus delta over 2 lies between f of c minus delta and f of c plus delta, plus epsilon, so that f of c plus delta over 2 is less than f of c plus plus epsilon, which is gamma. Okay, but this means that c plus delta over 2 is in the set S. This is the contradiction. prediction. Since C is an upper bound R of S for S. Now suppose that f of C is greater than gamma, and let epsilon is f of C minus gamma greater than 0, is f is continuous at C. There exists delta greater than 0 such that x minus C, absolute value of x minus C is less than delta, then absolute value of f of x minus f of C is less than epsilon. So whenever C minus delta is less than x, which is less than or equal to C, we have f of x is greater than f of C minus the epsilon, which is gamma. This means that none of the real numbers between C minus delta and C lies in S, which is to say just to say that C minus delta is an upper bound for the set S. And this is also a contradiction. Contradiction is C is least upper bound of S. Okay. Now we have shown that both of the assumptions we have shown that both of the assumptions f of C is less than gamma and f of C is greater than gamma leads to a contradiction. So we conclude that f of C is nothing but equal to gamma as required. And we have proved one part. Now the case where f of A is greater than f of B can be deduced by considering the function g of x is equals to minus f of x, and we have g of a is less than minus gamma, which is less than g of b. So from what we have already proved, there exists C between A and B such that g of C is minus gamma, which means that f of C is gamma. And this proves the theorem. Okay? This proves the theorem. Now here we will end our this part of the lecture, and then in the next part we will talk about the existence of nth roots of unity, and then we will give a special case of the fundamental theorem of algebra, and then we will end this book on the concise introduction to the pure mathematics. Thank you so much.